Okay, continuing on in section 1.5, we're going to talk about the building blocks of matter and what laws came from some research through a very long time ago. So at first, back in like 370 BC, this was the first idea that matter was composed of small, indestructible particles. What I really find amazing about this is that you think about how long that was ago, that people actually thought to go that deep into science, because they certainly didn't have any technology. Anyway, so in this idea was that matter was composed of small particles that were not destructible or indestructible, excuse me. A little later on, Plato and Aristotle came along, and they agreed that matter, or they held that matter had no smallest parts. They proposed that different substances were composed of different proportions of fire, air, earth, and water. Then came John Dalton. John Dalton's kind of the one that has established basically all what we know about the building blocks of matter. He came up with the atomic theory of matter, and he supported the earliest ideas that matter was composed of small particles that were indestructible. From John Dalton's work, we were led to the modern atomic theory and its laws. There's three laws that we're going to define: the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. But first, let's look at Dalton's atomic theory. Dalton's atomic theory explains a few things. It says that each element is composed of tiny, indestructible particles, which we know to be atoms. Atoms of a given element have the same mass and the same properties. That means if we're talking about helium again, one helium atom versus another helium atom, they're going to have the same mass and the same properties. You won't be able to distinguish between the two of those. He also said that atoms combine, and when they combine, they do so in whole number ratios. And when we have that, that's something called water, that's something called a compound, like water. So if water, oops, sorry about that. Let me go back. Right here. Like water, this would be your whole number ratio. So water, again, is always 2 hydrogens to every 1 oxygen bonded together. And fourth, he said that atoms of one element cannot change into atoms of another element. And that is true under normal circumstances. So if I have a helium atom, I have a helium atom. That doesn't mean it can't be by itself at the beginning of a reaction and be bonded with something different at the end. It just means that I'm going to have that element and you're not going to change it. Okay, the law of conservation of mass. This is that in a chemical reaction, matter is neither created nor destroyed. So what that means is if I start with one thing, I'm going to end with it. It may look different. So for example, if we take a look at this experiment, here I have sodium. Sodium is a metal. It's actually a very soft metal. You can cut it with a butter knife. It's also very explosive. And then here I have chlorine, and it's chlorine gas. So there's a gas inside this Erlenmeyer flask. If I take those two and react it, I get sodium chloride, which you know is table salt. So here you're taking, crazy enough, a soft explosive metal with a gas and making table salt. But the point of the law of conservation of mass is that if I start with sodium, I'm going to end with sodium. And it looks different. Here sodium is an element. It's by itself. Here sodium is part of a compound. But it's still there. Okay. The next law, the law of definite proportions, is that all samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. Again, this goes to water, and we're going to use water as an example here. All right. The decomposition of 18 grams of water results in 16 grams of oxygen and 2 grams of hydrogen. The oxygen to hydrogen mass is 8 to 1. What the law of definite proportions is saying is it doesn't matter how much water we have, that oxygen to hydrogen mass is always going to be 8 to 1. Does that make sense? Then we have the law of multiple proportions. This is when two elements form two different compounds. The masses of element B that combine with 1 gram of A will be expressed as a whole number. Okay, so that is a little confusing, I think, but here's just what it means. It means that the law of multiple proportions is when I have two atoms that are put together, I'm going to have a ratio here. And that ratio can be different. So A could bond with B, but it could also bond with two B's or three B's. So that's where the multiple part comes in. So these are the two compounds, or the two elements that are the same, A and B, but they have different proportional relationships. Here's a real life example of that, which you would be familiar of. So carbon dioxide looks like this, CO2. So law of multiple proportions is looking at, okay, I have these two atoms, they're put together, it's 1 carbon to 2 oxygens. Then I have carbon monoxide. It's the same two atoms put together, but in different proportions. So you have 1 carbon and 1 oxygen. But, and so that's your law of multiple proportions.